All right, good morning, everybody. Today we will continue our discussion on multiple expansion, which is a technique we can use to solve potential problems. Before we talk about how do we use that technique, we introduce the concept of the dipole moment, which is a vector P is defined as the sum of all the charges, individual charges, multiplied by their each individual location at Ri. And it turned out we have calculated the potential due to a dipole distribution, right, when they're located at d/2 across the origin.
Hey, Dr. Ryan, are you sharing a screen besides welcome to your new iPad?
Oh, no.
I think we're seeing the, oh, no, you're not?
Oh, okay. Yeah, let me know. Thank you for letting me know. I have to see if I could make this disconnect and put it back. Okay. All right. Thank you for letting me know. Okay, so this is the dipole moment, right? This is where we left off. We simply calculate dipole moment by multiplying the charges by their location. And this one, I want you to pay a little bit attention. You have a positive 2q, but you have a negative q. Okay, now we move them. They are not symmetric around the origin. In this case, they are. And the negative q is now at the origin. Okay, so now let's look at just one more case where you have the same charge, positive 2q and negative q, but let's move them back to symmetric around the origin. And I'm asking what is the dipole moment of this system? Okay, again, you have your definition, so you should be able to find out what your dipole moment is. So I'm gonna go ahead and let you vote on this. I'm not gonna let you go to the breakout room, but simply just take out a piece of paper and do a little bit computation, and you should be able to find out the result. Okay. Don't vote, don't just think what it would be, actually calculate it, okay? All right, so we'll run for another 15 seconds. So if you haven't voted, please do so. Okay, all right, any last minute vote? All right, then I'm going to go ahead and end it. Let's take a look at your results. Okay, All right, so there's a little bit of variation. Majority voted for C, and there's still quite a bit vote for B. And if we're still B, it's the same as before we shifted the origin, right? It just shifted by d/2 in the z direction. So as we put in a mental note earlier, do you think the dipole moment could depend on your choice of the origin? Now we had looked at a couple examples before and it didn't. Now let's see if that's still the case. So we can simply calculate this dipole moment by adding up all the charges. One is 2q, positive 2q, and that's located at d/2 in the z direction. So I'm going to multiply by that r1, right? And you have plus the another charge is negative q, and it's located at negative d/2 z hat. So the first term becomes qd z hat. The second term becomes positive 1/2 qd z hat. So it becomes 3/2 q d z hat, and that is the d vector you have just defined, which is pointing from your negative charge to the positive charge. So it's going to be 3/2 q d. So the C answer is correct. Very good job. So at this point, you might say, aha, I found a counterexample where the dipole moment does depend on your coordinates. But previously, remember, we had, if I bring up, let me see if I can bring up that. Question we did. Is this, right? We looked at, okay, this is QD, positive Q, negative Q, and we moved them to a random origin and it's still QD. So now we have a situation that's no longer the same dipole moment. So taking a look at those two situations, what do you think that has changed? So if we try to answer this question, does dipole moment depend on the choice of coordinates? What would your answer be? Would you say yes, it does, or would you say no? Or you might say it depends. So which one of these do you think?
I'm arguing that it depends on the amount of charge that you have.
Okay, so what about the charge?
Depending, well, in the questions that we answered before, both charges have had the same value, and the question that you just threw at us, the two charges did not have the same value.
Yes, that's very good. That is precisely the difference between these two situations. So it turns out, normally when we say a dipole, we meant the positive Q and negative Q are of the same charge. But in this case, we have them of different charge. It is still a dipole, but however, the dipole moment is ill-defined. So you can see the total net charge, if we positive Q, negative Q, the total charge is net 0. And that is a well-defined dipole. But if you have a positive Q, a negative Q that's not of the same amount of charge, then the total net Q is not equal to 0. In that case, you have a dipole moment, which is ill-defined. When it's ill-defined, you can still calculate it, but it's going to depend on your choice of the origin. Okay, so the 3/2 is different from the 2QD that we just computed, which is different now. Okay, so now let's go ahead and try to look at another question before we introduce the multiple expansion method. So previously, we have derived an equation for the dipole. That's this expression, right? The dipole moment dot into r hat. Do you still recall this expression isn't exact, or if we did use approximation, what we use? I know that you probably still remember we said r is much, much larger than d. So this expression is an expression we derived at the approximation for valid for large r. Okay, so that's for a dipole source. If you have a dipole source, you can use this expression right away when you are far away, of course. Now let's look at another one. This one, I do want you to go ahead and vote on this. If you have a physical dipole a finite space d apart, what about this expression? Okay, is this expression exact or is it valid for large or small r? Okay, I'll give you maybe a minute in your breakout rooms, and if you come back, we can vote on this. All right, seems like I gathered majority of the vote already. Just any last minute vote at this point? All right, so if not, I'm going to go ahead and close this. Very good. I'm glad that you recognize this expression as something we can always fall back on, the exact expression everywhere, because this expression is simply using direct integration to calculate your potential. So given any kind of charge distribution, you can always add the charges one by one. Now, if you have continuous distribution, you do the integral one by one. It's not always the most simplest method. It's oftentimes the most difficult method, but it's always exact. And if you can't do it by hand, eventually you can still use a computer. So this method is universal and it is an exact expression everywhere. So we'll try to start out with this expression and see how we can simplify a charge distribution and calculate the potential using a multiple expansion method.
Dr. Ryan, can I answer a question real quick?
Yeah. Go ahead.
For the summation that we have in our potential, can we not replace that with an integral?
Yes, we are.
Okay.
Yes, exactly. It's either going to be a summation when you have discrete distributions, But if we have a continuous charge, that's like the one we are working on, it's going to be integral. Okay, so here we have some charge distribution, and let's say we take out a small cube, infinitesimal small, but obviously I draw it really dramatic, so it looks pretty big, with charge density rho, and is located at some location R prime, that's your source, and you wish to evaluate your field at this point of interest, and that is R. And of course, from your source to your field is your script curly R. And R prime makes an angle of theta, theta prime in this case. So as we recall, this expression is exact. And in terms of continuous distribution, the summation becomes a integral. So you're integrating all the charges, right, and over the script R. So let's see what can we do by doing some approximation. If we are looking at a place far away, then R prime over R is something that's really small. It's a very small quantity. We call it epsilon. And the script R, we need to work out the expression for R. So look at the laws of cosine in this triangle. So R squared is R squared plus R prime squared minus 2R R prime cosine of theta prime. Okay, so as you can see that our technique is whenever we can expand it using approximation, we always want to make the small number to show up. So how do I make it to show up? I need an R over R, R prime over R. So I'm going to say I'll take R squared out of the parenthesis. Then the first term becomes 1, the second term becomes the small number I'm looking at. Third term will have 2 R prime over R cosine theta prime. Right, so you manipulate it to be whatever you need so that your epsilon showed up. So that if you're looking just plain, the R is square root of all of that is going to be R, and square root of 1 plus epsilon squared minus 2 epsilon cosine theta prime. Okay, so you can see that we wanted to plug it into the denominator to get our potential. So that becomes 1 over R and 1 plus epsilon squared minus 2 epsilon cosine theta prime negative 1/2, right? It's on the denominator. Okay, so we recall, how do we expand this whole thing? Because 1 plus a small quantity, since we already use epsilon, I'm now going to use eta to represent the small quantity. To the power of negative 1/2 is 1 plus negative 1/2 over 1 factorial eta plus 1 negative 1 over 2 negative 1 over 2 minus 1 divided by 2 factorial eta squared. Now you can do the third, but we're not going to do the third term, just the first 3. So recall that relationship, so we can expand this. Now in this case, this entire thing is our small quantity yet. Okay, so 1 over R is going to be 1 over R, little r, of course, and then you expand this term. First term becomes 1. And second term is negative 1/2 times the small quantity. In this case, my entire small quantity is this guy. Let's circle it. Epsilon squared, negative 2 epsilon cosine theta prime. All right, and third term is going to be 3/8. Calculate this, it turned out to be 3 over 8. And the small quantity is squared, right? So the second term, the third term is going to be this squared. And there are higher order terms, but I'm not going to write it anymore. Okay, so you end up with some 1 epsilon or epsilon squared. So let's group all the epsilon together and all the epsilon squared together. So we will collect all these terms. and it becomes these 2 pages will not show up. So it becomes 1 over r 1 plus epsilon cosine theta prime 1/2 epsilon squared plus 3/8 times 4 cosine theta prime squared epsilon squared plus even higher order terms to the epsilon cubed. Because I don't need it, I'm not gonna bother writing it out. So this is order of epsilon third. All right, so just one more step. Okay, so this is the first order, this is the second order. Okay. Can't make this to go up, but let me add another page here. Hopefully I can bring it up. Okay, so now we have another page. All right, so let's finally, we're ready to plug this back in to get our potential. So recall our potential is 1 over 4 pi epsilon naught this over the script r. Okay, so and 1 over r now is being expanded. We're ready to plug it in. Okay, so v is going to be 1 over 4 pi epsilon naught. So see, the first term is just 1 over r. Okay, so I'm going to plug it in. It becomes rho d tau over r. So approximately, of course, because I already get rid of the other higher order terms. So you can see that this will be the largest leading term. This is smaller. This is smallest out of the first 3 terms. So let's look at them one by one. The leading term is going to be 1 over 4 pi epsilon naught, simply is d rho d tau over r. Now, of course, you're not integrating your field, and this is independent of your charge. So you can also write this in terms of 1 over 4 pi epsilon naught, 1 over r. Well, let me just put it together with 1 over 4 pi epsilon naught rho d tau. Okay, so that's your first term. I want you to look at this and think about what it means. What is the meaning of this integral?
That's your total charge.
Yeah, that is my total charge, Q total. And what does leading term tell me? So this leading term is in the format of 1 over 4 pi epsilon naught total charge over r. Does that look familiar?
It's the potential of a point charge.
Yeah, so this is a potential of a point charge. Very good. So we call this is our monopole terms, because if you're from far away, this charge distribution, actually, whatever charge distribution you're giving looks like a point charge from far away. And the point charge potential, KQ over R, is going to be the dominant term for the potential of that distribution. It's may not be exact, but it's going to be dominant. And if you have a Q total of a charge distribution that's not 0, you have net charge, then from far away, you're definitely going to have a monopole term as your dominant leading term. Okay, so that's what we mean by multiple expansion. Here we have the multiple term. You probably can predict what's coming up next. We're going to look at the second term. So next one is this. All right, we can plug in back our epsilons. Rho d tau over r. And recall epsilon is r prime over r. So I'm going to put it back times cosine theta prime. Okay, so again, r is not something you need to integrate over. R is your field, right? You're integrating over the prime term. So I'm going to write the r squared, 1 over r squared in front. And what you're integrating over is rho. Rho is actually a function of r prime. It could be a function of r prime, or it could be uniform, times r prime times cosine theta prime times d tau. So this is what you need to integrate over. And you can see this terms is different from the other terms. Instead of 1 over r, is 1 over r squared. This will drop off faster than the first term. Okay. And care to guess what all of this is? The physical interpretation of this? What is the physical meaning of this term? So I want to recall something we did in the previous class is we have derived this, this formula. Okay. Remember, this is a potential due to a dipole at far away. And it does have a 1 over r squared dependence. Okay, so this first term is a total charge and I give you the monopole term. What do you think the second term will give you?
The potential due to a monopole, or I'm sorry, a dipole.
Yes, so this is a potential due to a dipole. Very good. This is your dipole term, and this is a dipole moment. So physical meaning of this integration is going to be your dipole moment. It turned out this might be looking a little bit more familiar, it will be able to, you can look at the physical meaning of that a little bit better. The dipole moment give you some idea of the charge distribution. It's a property of a charge distribution. It does not depend on R. It does not depend on where you are evaluating your field, but it does depend on the angle between your charges and your so this angle is between r prime and r. So dipole moment is regarding the charges, yes. So it doesn't depend on the quantity of r, but it does depend on where you are evaluating your field. And it is describing the charge distribution in the sense it can be orientation dependent. It can be depending on your choice of your coordinates. When you're especially when your total charge net is not 0, then the dipole moment is not well defined. Because if you change your coordinates, you have changed how charges are distributed around your origin. So you should expect your dipole moment to change. Okay, so this is a feature describing charge distribution in general. If people ask you, what does dipole moment tell you? You can say, well, it is describing a property of charge distribution. Okay, so you can see that given whatever charge distribution, we are starting off with a very general situation. But from far away, we can always approximate your charges, the potential, by looking at your leading term and your monopole term and your next term, which is dipole term.
Dr. Ryan, I didn't quite understand why our potential due to a dipole describes a property of charge distribution.
Okay, so Charge distribution, meaning that where charge is, distribution is, okay, I got this charge located here, and I got some more charge located there. So that's what I mean by distribution, right?
Mm-hmm.
So you can see in this expression, you have, well, you have some density at some location, at some angle. So that's sort of a description of distribution. Where do you have what density where?
Okay, thank you.
Okay, thank you for asking that. Okay, so that's our first two terms. We still yet have one more term coming up. The third term, let's work it out. Third term is 1/4 pi epsilon naught rho, rho as a function of r prime d tau over r. And let's recall what this third term is all of this. So I'm going to plug it in. Okay, 1/2 plus 3/2 cosine theta prime squared, and you can see what we got. We got a epsilon squared. So epsilon, recall, is r prime over r, right? So it's going to be r prime squared over r squared. So this is our third term. Again, r cubed, I'm going to move it outside of the integration. I get 4 pi epsilon r cubed. So what we are integrating over is rho r prime squared. And this entire thing d tau. So at this point, you probably already noticed a pattern. You also combine it to look at with what we had previously. Here, you just have a cosine theta. That looks simple enough, right? Here, you have something more messy. But you realize there is some math function that can be used to replace those terms. It turned out that you still recall that P1 of cosine theta for Legendre polynomials is exactly cosine theta, right? And P2 of cosine theta is exactly 3/2 cosine theta squared minus 1/2. So those are Legendre polynomials. So we could have write this in something more similar or simple format. So we can replace all of that with simply P2. D tau. Okay. Of course, here you could have rewritten this using P1, but cosine is simple enough. You can just leave it as is. Okay, so you can see, again, you can see the potential, leading potential is 1/r, the largest. The dipole potential, the potential due to the dipole is 1/r squared, is second order term smaller, drops off faster. The third term is 1/r cubed, it's even less, right? So anybody would like to guess what we have here? What is the physical meaning of that? Your total charge becomes, the second term is a dipole moment, and the third term becomes?
Professor, isn't that quadrupole moment?
Kenneth, very good. It is a quadruple moment. Okay. So you can see that we, for whatever potential, it goes like this. Multiple expansion is Q total over R. Simply, this is a monopole moment, a monopole term, the potential due to a net charge, dipole, second terms, over R squared, plus the quadruple term, R cubed. Now you can have even higher order terms, and if you can calculate everything, but that's going to be forever. then it is the exact expression. But oftentimes we just need the first few terms, that is the dominating, and that's good enough for us. If you have your Q net, which is 0, if Q total is 0, then obviously the dominate term becomes the dipole term. The first term goes away. The dipole term is dominating. Okay. If your Q net is not 0, then your monopole term should be dominating. If both your monopole and dipole term is 0, then quadruple term will be dominating. Okay, so you might wonder, what does it look like if I have a Q net is 0 but dipole is not 0, and what does it look like if I have dipole 0 but quadruple is not 0? So we will going to look at a few more examples and make sure we understand that properly. Okay, so I have a few of these questions coming up. So there are 4 different charge distributions. Okay, from far away, which one do you think will produce a potential that looks like some constant over r squared? Okay, I'll give you some time to discuss. We have maybe 4 of these questions, so we will go through them one by one. Okay, you can take a screenshot before you go, and we will discuss later.
I mean, this may be the point of the question, Dr. Ryan, but when you're saying that when one of these terms is 0, the following term dominates, what about the term that follows that? For example, if we have a monopole that is 0, a dipole would dominate, but a quadruple term, would that still be, I don't know, important? I mean, in the math, yeah, it's important, but I mean, physically.
Well, physically, you probably won't care if you just want the dominate leading terms.
Okay, got it. Thank you.
Okay, I've gathered majority of the vote. 5 more seconds for any last minute vote to come in. All right. Okay, I'm gonna go ahead and close this. Let's take a look. Okay, here's our results. We want to find a distribution where produce a potential looks like 1 over r squared dependence. So 1 over r squared for potential is that, does that look like a monopole term or dipole term?
Dipole.
A dipole term, very good. Okay, so let's go through them one by one. What will A give us?
A monopole.
So this would just be a point charge distribution, a monopole term. Just going to be KQ over R. KQ over R. Second one is 2 positive 2 Qs split for little distance.
Still a monopole.
Yeah, still monopole. You still from far away, they look like positive 4Q combined. So it's still a monopole dominate. You're not going to have 1 over r squared from far away. C.
Dipole.
Okay, so C is a dipole and they are 4 charges. So exactly what kind of dipole am I looking at? What is the direction for my dipole moment? Might be easier to look at your dipole moment. Previously, we did QR. When it's, so is this dipole moment well defined? Or ill-defined? When the net charge is 0, then it's well defined. Is the net charge 0?
Yes, it is.
Yes, very good. So so it's well defined, and that's going to be QD by from your for a dipole, it's going to be from negative charge to your positive charge. Okay, so for each pair from negative to positive, from negative to positive, so it's like you have those 2 of those dipole moments, right? So the total dipole moment add up to be from pointing bottom to pointing upward from negative to positive Q. So yes, this is 1 over r squared. What about D?
It's ill.
D, let's look at the overall charge, right? Positive 2Q, negative 2Q, positive Q, negative Q. So this is indeed a dipole because total net Q is 0. So you're not going to get a monopole term from far away, and you will have a dipole term. But let's look at in which way this dipole moment will be pointing at. So how do we form dipoles here? So I could choose a well-defined pairs where you have a positive and a negative. So positive 2Q and negative 2Q. I can choose to look at this pair that give me a dipole moment pointing this way, right? And I can look at the other pair that give me a dipole moment pointing this way. So overall, they will add up to be somewhat diagonally, but maybe not exactly in the middle because one of the dipole moment is a little bit bigger with 2 Qs. But overall, I will have a overall dipole moment, and that will give me the potential 1 over r squared from far away. Very good. So C and D are both correct. So we'll just choose E because more one of these is correct. Okay. Now, let's continue to do more practice. So here we have slightly different arrangements. Again, I'm asking for 1 over r squared. So again, you're looking for dipoles, okay? And go ahead and take a screenshot. Again, I'll give you some time to discuss. All right, 10 more seconds. Okay, any last minute vote? All right, I'm gonna go ahead and close this. This time we seem to be in more of a agreement. Majority of you chose that either none of those or more than one of them. Okay, so we can look at them one by one. So A will give us what kind of potential from far away?
Monopole.
Yes, it will be a positive Q overall, right? So you have a Q net is not zero, so it give you a monopole term from far away. Very good. That is the dominant term. And B, what would B give me?
The dipole.
This is a dipole, very good. So B is the one we want. And what about C?
I'm arguing that it's also a dipole.
So let's look at, so I have two pairs, right? One is from negative Q to positive Q, the other one from negative Q to positive Q. So no net charge, so we don't have multiple terms. In terms of dipoles, what do you think? Do we have a dipole term?
It doesn't look like you have a dipole term just looking at how you drew your dipole vectors.
Yes, in this case, I don't have a dipole term because you can see these two dipole moments are exactly equal opposite direction. So dipole terms cancel out. We do have a quadruple term. So this one from far away, you will get a quadruple term. But that's not what we want. D. So we have,
Dipole.
yeah, it's a dipole. Net charge 0. We do have positive charge, negative charge split by the distance. As we said for dipoles, you just need you can look at the average position of your negative charges. In this case, my average position is sort of in the middle. So I know my dipole moment is going to be pointing upward. So I do have also a dipole term for D. So yes, B and D are both correct. Now you chose E is the correct answer. Very good. All right. So more of these type of questions. Here we are looking for, again, the dipole term being the leading contribution, non-zero contribution. Okay, so there are 5 of these different distributions. Again, I'll give you some time to discuss, okay? Okay, 10 more seconds. Okay, I'm gonna go ahead and close this. We will take a look. So this is our results. We have 5 different scenarios, and we want to find again the dipole term being the leading term. So the monopole term should drop. Okay, so let's look at them one by one. And choice A, do you think this will give us a dipole term?
Yeah.
Yes. So which direction do you think the dipole moment will be pointing
We had that was what we were trying to figure out. Liam argued it pointed to the right, and then I argued it was pointing straight up.
at? And why is that?
For the ones straight up,
Either one.
let's do the simplest one. So if it's pointing to the right, we would just notice the dipole moment between our top pairs of positive and negative charge is pointing from the negative charge to the positive charge. And then the same thing would happen right below it. Those 2 pairs are going to point from the negative charge to the positive charge.
Okay, I see. Okay, I see a hand up. Nicholas, do you have a question to ask?
Yeah. So is A also a quadrupole or is it just a dipole? I'm kind of confused on
A
what's what.
dipole. So the average position for your negative charge is here. The average position for your positive charge is here. So you should have a dipole moment pointing to the right. I understand there are different ways you may want to look at this, right? So you can do, okay, I have first pair is pointing this way, another pair pointing this way. And then give you to the right as well. So how do we get it for the pointing up? Sorry, I don't that.
Yeah, it's just the diagonal from your positive Q to your negative Q.
Didn't that give you to the right as well?
Yeah, it did. Now that I drew it out on a piece of paper.
So this one is a dipole that we want. What about B? B give us what term from far away as a dominating term?
A monopole.
So it's going to be Q net as in 5Q, 4Q. And what about C? Also a
It's a monopole.
total net is going to be 3Q. And D, again, it's a monopole because this is positive, this is also positive. Even though we don't really know exactly how large this is, it's going to be. D, E might be the one that's more interesting. What do you think about E?
it behaves like a cosine function. So you're going to have half of it as positive and half of it as negative.
Ah, yes, very good. So which half is positive?
From 0 to pi, and then is positive, and then from pi all the way back to 0, it's going to be negative.
Okay, so yes, cosine would be like this. From 0 to pi over 2 positive, from pi over 2 to pi is negative, and theta is measured relative to the z angle. So this half, this quarter and this quarter are both going to be pi over 2. They're both pi over 2 from z, right? So they are both going to be positive. The bottom half going to be negative. Okay, so E also turned out to be a dipole. It's as if, so you have a induced charge distribution and it behaving like a dipole from far away. Okay, so E is also correct. So D, A, and E both correct. Very good. So now let's actually work out E. Let's work out this problem together.
Dr. Ryan, do you mind putting the microphone a little closer to you?
Okay, yeah, I had it on full volume. I'm just gonna move myself a bit closer. How about now? Can you hear me now?
It's a little better.
A little bit better? Okay. All right. I'll try to be as close as I can. Okay, so we're looking at this example. Positive on top half, negative on the bottom half. And this is sigma naught cosine theta. I want to work out the potential using multiple expansion. Okay, so this is the example we're going to do. And looking at our potential, you realize that it used volume density instead of surface density. So can we rewrite this using volume density? And if so, how do we write it? Anybody have some thoughts? How do we write the volume charge density for a surface distribution?
I want to say it's sigma d tau, but I feel like I'm just kind of
There is an important function we learned in the very first chapter.
Is it a delta function?
The delta function, yes. So when we have, let's say, a surface density that's just simply not across the volume, but we want to force to write a volume density, we need delta function. Likewise, line density, you need a delta function. A point charge, you want to write the volume density for a point charge, you certainly need the delta function, right? And for a point charge, is simply Q delta, the three-dimensional delta function. So here we have surface density. So how do we construct this delta function? We know that these terms should probably carry over to my density. And this is telling me you have this kind of surface charge at certain location. And the delta function will tell you the location, just like how this one tells me there is a charge located at r equals 0. So that's what this delta function is telling me. So how do I make this delta function tell me where the charges are? Sigma, I see as Nicholas wrote sigma delta z. So z as in what direction then? We probably need the spherical coordinates, right? So how do we represent? I mean, this z is one axis. My charges are located all across the surface area. So what do I do?
would it be del r del phi del theta?
We do need delta, and how many? And think about this. Okay, I need rho. Okay, yes, in terms of theta phi. Let's think about what the meaning of where the charge is located. Okay, so Benjamin said wouldn't be r minus capital R. Let's see if this is telling me where the charge is located. Here, this tells me this located r equals 0. This is telling me when r is equal to r, this is non-zero, right? is infinity, but when r is not ln r is 0. So this does tell me the location of the charges. So this is telling me the charge is located at r equals r, which means that is the shell. Very good, Benjamin. That is what we want. Okay. So this is simply our volume density for our potential. So we're going to use them. Okay, so for the monopole term, first term is the monopole term. You know it's 0. I know you know it's 0, but let's say pretend we don't know, and we're simply using monopole expansion to evaluate our potential. First, this is our first term we want to see. First term is kq over r, the total charge, rho d tau. And let's calculate this total charge. It's going to be sigma naught delta. Sorry, I should put prime on everything. And d tau in spherical coordinates is r prime squared sine theta prime dr prime d theta prime d phi prime. And you can see sigma naught is a constant. I'm going to take it out of my integral. This delta function, I can use the delta function to do this guy. This will, so remember the fx delta x minus a dx is the fa, right? You're picking out only just the x equals a. So here you're picking out only r prime equals capital R. So this term becomes what? R squared. Okay. All right, and the next integration is going to be cosine theta prime sine theta prime d theta prime and d phi prime. Okay, d phi prime simply 2 pi, that is easy. And this term is from 0 to pi. So this one becomes sine theta prime d cosine, sorry, d sine theta. Right, because d sine theta becomes cosine. So that's why I can combine cosine and d sine, become d sine theta from 0 to pi. And that becomes 1/2 sine theta prime squared from 0 to pi. Evaluate that. It turned out to be 0, as you can see, right? Okay, so this whole thing is 0. It dropped as expected, as you might expect, because you can see this is a uniform distribution. No, it's the sigma is constant, but they're how the charge are distributed. The top half and bottom half is exactly the same way, follow the exactly same cosine, but just opposite sign. So it makes sense that they drop. Okay, so what we do need is a second order term that is the dipole term. So the dipole term is 1/4 pi epsilon r squared, and then the dipole moment. The dipole moment is this guy. So let's calculate it. Plug in rho delta cosine theta, and you still have this r prime cosine theta prime. D tau is that long thing, is r squared sine theta, dr, d theta, d phi. Okay, so now I'm going to group everything together, right? Now you group all the r together, you get delta r prime minus a minus r prime cubed, dr prime. And you have a d phi is also the easier one. This one gives you r cubed. The d phi give you 2 pi. The one that's a little bit complicated is the theta one. So it's going to be, so look at this. So how do we do the integration? It seems like I have a cosine squared, and I can write this in terms of the negative d cosine theta from 0 to pi. Okay, and that becomes negative cosine theta prime cubed divided by 3, evaluated from 0 to pi, and that gives me 2/3. Okay, so putting everything together is going to be r cubed sigma naught 2 pi 2/3, and that is 4 pi sigma naught r cubed over 3. So your potential, I can say my potential is approximately going to be kq over r squared times the dipole moment, and dipole moment we just calculated is all of this, so it's going to be sigma naught r cubed over 3 epsilon naught r squared. So you can see that's how we solved this problem using a multiple expansion method. You probably have seen this example before, right? And we just solved it using multiple expansion. Is relatively fast. You can see first term goes away, and the leading terms is going to be the dipole term, which is this result. Okay, so that's just a way to show how you're going to use this to solve problems. Okay, any questions at this point on this particular problem?
Professor, can you scroll down again?
Yeah, here or the second?
Yeah, for the second term, just a little bit further to the final answer. Yeah, thank you.
Any questions? Okay, if not, I have one last question. I'm just gonna walk you through it here. One last question again, in terms of multiple expansion, right? Our method is expanded using the multiple term, if any, dipole term, if any. If none of those, you have to go to the quadruple terms. So for the following charge distribution, what are we gonna have? These darker charges represent the positive Q, and you have lighter blue is negative Q. So let's look at this, right? You have equal number of positive charge as in negative charge. So your multiple terms should be 0. And dipole terms, let's look at dipole terms. We can do them one by one, right? So this pair going positive, negative to positive, that's the dipole moment. This term going negative to positive, the dipole moment. And this one going to be negative to positive, the dipole moment. And negative to positive dipole moment. So it looks like the dipole moment cancels out as well. So my dipole moment, dipole term should be also 0. Again, dipole moment describes certain kind of charge distribution around charge distribution, where charges are located. In this case, it looks like they're evenly sort of located around the center. Dipole terms goes away. So it looks like in this case, I'm only going to have the higher order terms, that is the quadruple term, that will survive from far away. Okay, so it will be D is the correct answer. Okay, so that's the last question. Any questions so far? All right, so that's all we have for multiple expansion. Starting on Wednesday, we will be talking about, so instead of chapter 4, we will do the chapter 5, which is magnetostatics. We're talking about the static time independent situation for magnetic B fields. Okay, so the reason for that is I want to group chapter 4 and 6, which is electric field in matter or magnetic field in matter, and do them together because they're very similar in terms of math and concepts. So I want to do those two chapters together, and also very selected. So we're going to do chapter 5 first, and then 4 and 6. So I'll see you all on Wednesday. Okay. All right. Bye, everyone.
Thank you, Dr. Ryan.
Thank you, Dr. Ryan.
Thank you,
Bye.
Dr. Ryan.
Dr. Ryan.
Yeah.
I I was writing stuff down and I didn't see why in the math the first term, the monopole term that we were figuring out goes to 0, like which integral makes it 0.
Me here. That
Yeah.
is sine theta.
Oh, I see.
Sine pi minus sine 0 squared. Yeah, so that goes over.
Okay, got it. Okay, thank you.